Thank you. So good afternoon, everyone. My name is Calcabrini. I'm an R&D specialist at PVcase. So for those who don't know us yet, PVcase is a software as a service company based in Lithuania. Our leading product is PVcase Ground Mount. It's an AutoCAD plugin that is used by more than 800 customers in over 60 countries to design utility-scale power plants. Next to that, we also have another AutoCAD plugin for the design of PV systems on industrial and commercial scale rooftops, and PVcase Yield, our own energy yield simulation tool, which is the main focus of this presentation. So in the next few minutes, I will be introducing you to the digital twin-based software ecosystem that we have been working on. Then I will present a brief introduction to our energy yield simulation tool. And finally, we will look into an accuracy evaluation study that we have performed on our tool using publicly available datasets. So as part of the Trust PV project, which is a project funded by the European Commission, we have been working on this standardized general digital twin concept to support all the life cycle stages of a PV plant. So we enable the creations of these digital twins using our design tool, PVcase Ground Mount, which is seamlessly integrated with our energy yield simulation tool, PVcase Yield, which allows to simulate the performance of this plant, eventually gain insights, and improve the design in an iterative process. So at the end of the day, a digital twin is nothing more than structured information, which must be in an open source format to serve as an integration platform between different services and processes throughout the life cycle of the plant, from design to construction to operation and monitoring. And the whole idea behind this concept is to have a unified source of information about the PV asset, where we ensure that information is preserved, is updated, and we track its evolution over time. So in the next few slides, I'm going to be showing you some visual representations of such digital twins that were created and simulated with our tools. But first, I want to tell you a little bit about our energy yield simulation tool. So PVcase Yield is the result of over a decade of development in cooperation with IMEC, a research center in Belgium. And at the core of our tool, we combine a ray tracing engine with a coupled thermal electrical model to simulate the performance of PV systems. So this allows our customers to develop and analyze layouts on arbitrary topographies. Also to simulate complex PV systems such as bifacial agri-PV systems. And eventually, we allow our users to optimize the performance of the PV system in space and time. And I can see the animation is not working, but basically what you're looking at here is a reconstructed digital twin using a drone service from a PV plant in Italy. And what we have overlaid on top of the digital twin is some information of the annual shading losses, and you can see how this depends on the slope of the terrain. It would be a bit more clear with the animation, but that unfortunately failed. So after running simulations with our tool, users can analyze the losses, time series, like they normally do. And on top of that, because our tool is cloud-based, what we are enabling is our users to run multiple parallel simulations without consuming resources in the local machine, which allows them to continue working on other tasks. So after this brief intro, what we will try to answer is how accurate is PVcase Yield. And for that, we have been working with two publicly available datasets. So the first one is this one that I'm showing here. So this dataset is owned by the Technical University in Denmark, and it contains a combination of fixed tilt and single-axis tracked system with monofacial and bifacial modules. For this plant, we have hourly data for power, irradiance, and temperature. And we also have a fair assessment of the system losses, which we have included in our simulations. So the first thing that I want to show you is how does our simulated irradiance compare to in-plane pyranometers. And for this comparison, we have switched off in our model the angular reflection model to emulate the measurements taken by a pyranometer. And what we found is a really high accuracy for the front side irradiance and a overestimation between 5 to 7 watts per square meter on the rear side irradiance. Now, in terms of temperature, in this case, we only had data for one of the 4 systems that I mentioned. And in this case, what we found is a slight underestimation of about 2.7 degrees. Now, what I'm showing here is a plot taken from this peer review study that is cited here, where the same data set that I just mentioned was used to benchmark different software. And what we have put on top of this is the results that we have obtained with our tool. And what you can take from here is that we are presenting relatively low errors in terms of DC yield, and with a slight tendency to being conservative, and that we are within range of the other software tested in this study. Now, the second data set that we have been working on belongs to NREL. This is of a test plant that is in Golden, Colorado. And in this case, the main difference is that we have minutely data for bifacial and monofacial systems on single-axis trackers. And also in this case, it was not possible for us to make a fair assessment of the system losses. So we have estimated that it's roughly 5%, but we're leaving it out of the analysis, so you can expect an overestimation in our energy yield calculations. So the first thing that I want to show you in this case are some time series. So first, in terms of temperature, here you are seeing for the bifacial row how our simulated temperature closely follows the variations of the temperature throughout the day, especially during daylight hours, which are the important ones for calculating an energy yield. And also in terms of power, we are following the trends, but here is, I come back to this point that I was just mentioning, you can clearly see this overestimation. And we have checked, and this overestimation is more or less in the range of the expected system losses. I'm just gonna show that in the next few slides. So in terms of irradiance, in this case, what we can tell is that when we go down to minute level, we remain in the same ratio of accuracy. So in this case, the maximum error that we are obtaining is for a bifacial module, and it's about 2.4%. And on the rear side, in this case, we have compared our simulated irradiance with the average of 4 reference cells that were placed along the long edge of the modules. And in this case, the maximum error is about 9%, which I have to say is remarkable when you consider that this is just the rear side irradiance and is isolated from the front one. Then in terms of temperature, in this case, we have information for the 4 systems, and we found that the errors are more or less consistent with what we had from the DTU study. So maximum bias was about 3 degrees. And finally, in terms of yield, so in this case, again, we're excluding system losses. And when we look at the errors that we're obtaining for most of the systems, you can see that the overestimation that we're giving is more or less in the range of these expected system losses. So this brings me to the conclusion. So to sum up, I have introduced this digital twin-based concept, which has the potential to solve many of today's challenges in PV simulation through enabled ray tracing. And it also has the potential to reduce the cost and increase the value of different PV digital services throughout the lifetime of the PV asset. Then I have shown you how we can implement such digital twins in an easy way, combining our ground mount tool with our energy yield simulation tool. And from the validation study results that we have presented, we have seen really good results for the front side irradiance and the rear side irradiance, both when working with hourly and minutely data. In terms of temperature, we found maximum deviations lower than 3 degrees. And when we have a fair assessment of the system losses, our energy yield error is between -3.5% and 1.4%. So now, going forward, what we want to highlight is the importance of the availability of such high-quality data sets to continue improving the energy yield simulation tools and increasing the confidence in our estimates. And this is especially important for large sites. So I invite you, if you are in the game, to approach me after this meeting or one of my colleagues and have some discussion about this. So with this, I come to the end of the presentation. So thank you for your attention.